And so again, this is stuff from chapter 14, not on the test. The example we gave in the book, this is homogeneous catalyst. It's formic acid decomposition. Formic acid, there's another name for formic acid. Do you know what it is?
Hydroformic?
Not hydroformic. Good try. Unfortunately.
Formaldehyde.
Formaldehyde, no. Formaldehyde would be missing this oxygen here. It has to do with the numbering and naming of carbon chains. One carbon is called meth. Not methane, but this would be methanoic acid. So, methanoic acid. Then ethanoic acid, propanoic acid, butanoic acid, depending on how many carbons you have. Well, formic acid can undergo decomposition, and it decomposes into carbon monoxide and water. What has to happen in a decomposition reaction like this is we have to break bonds and we have to rearrange electrons. Now, breaking the bonds and rearranging electrons, is that something so easy to do? No, not really, because we got to get this hydrogen over here and do some other stuff. You know, one of the ways we might be able to get that hydrogen over there is by this. If you can imagine, you know, formic acid, this carbon should be sp2. sp3 carbon, or oxygen, sorry, sp3 oxygen, and then this is a hydrogen, an S. So one of the things you might imagine happening is this. You know, this sp3 lone pair gets pushed into the s orbital of hydrogen. If the sp3 gets pushed into the s, then we form an sp3s orbital overlap, which results in a bond. But can we have two bonds to hydrogen? No. And so what that has to do is it has to kick out these sp2 electrons here and place those over here. If you were to describe this reaction, what kind of reaction is this? Would you say it's a redox reaction or a what kind of reaction does that look like? Well, let's look at the overall reaction. If we look at the overall reaction, is that a redox reaction, acid-base, or metathesis? Acid-base? Metathesis, I would rule metathesis out because metathesis would be ion combinations, and we don't have much in the way of ion combinations. So it's either redox or acid-base. It's hard to tell, but if it were redox, then we should see that the oxidation states change. And so let's go ahead and figure out all the oxidation states here. What's the oxidation state?
Carbon is 4.
You guys remember how to calculate the oxidation states? We just do a tug of war. Hydrogen versus carbon, who wins? Carbon. So carbon takes those two electrons. Carbon versus oxygen? Carbon versus oxygen? So carbon only ends up with two electrons because oxygen took all the others. Does that make sense?
Yeah.
How many electrons is carbon supposed to have? 4. It only ended up with 2. That means it's 2 electrons short, which means we give it a negative or a positive charge?
Positive.
Positive. And so this is going to be positive 2. 2 electrons short. Hydrogen has none. It's supposed to have 1. It ends up with 1 electron short, which means plus 1. This oxygen? It's got, now it's taking these two, so it's 2, 4, 6, 8. Oxygen normally has 6, has 2 extra electrons, which means
Minus 2.
2. This one, these 2 get pulled to oxygen, these 2 get pulled to oxygen, so oxygen ends up with 2, 4, 6, 8, minus 2, and this hydrogen ends up with none.
Plus 1.
Plus 1. Okay, let's go over here and figure out the oxidation states. Carbon versus oxygen. Oxygen wins. And that means carbon ends up with just these 2 electrons here.
It should be 4, so that's
It should be 4, and we get a plus 2. Oxygen gets these 2, 4, 6, and has these 8. So 8 electrons
minus 2.
minus 2. And then hydrogen versus oxygen. Oxygen takes all of them. So oxygen gets 2, 4, 6, 8, minus 2. Hydrogen gets none, which is plus 1 and plus 1. So did the oxidation states change?
No.
No, if the oxidation states don't change, then this is not a redox. This must be a acid-base reaction. Now, is this a Bronsted acid-base reaction or Lewis acid-base reaction?
Lewis?
Well,
You're not going to
yeah, because in a Bronsted acid-base reaction, let's say we reverse this. If we reverse this reaction, are we just getting a proton donor and a proton acceptor? It's Bronsted, right? Bronsted acid is a proton donor. Bronsted base is a proton acceptor. Does it look like just a simple proton transfer reaction to you? No. This has got to be a Lewis. Now, what is a Lewis acid-base reaction? No, not electron transfer. A Lewis base is a electron pair donor. What's the difference between transfer and donor? Well, transfer is more the electrons are totally lost and someone else gains the electrons. So a transfer would be more like a redox reaction. If carbon went from plus 2 to plus 4, then it lost. It was transferred. But in this case, electron pair donor, electron pair acceptor, and what happens is this. You know, when we look at the oxidation state here, did the oxidation states change? No, the oxidation states are the same, so this process here is not a redox, you know, going from this to that. What is it? Well, it's a Lewis acid base, right? That's what we determined. And so how is that a Lewis acid base?
Deprotonation of the...
Yeah, the deprotonation of this carbon here. How is this Lewis acid base? What's acting as the acid? Because this is just formic acid, right? So formic acid is an acid. Where's the base? So this gets a little bit tricky because normally we think of formic acid as an acid because this hydrogen is what we call an acidic hydrogen. This hydrogen is a acidic hydrogen as well? No. Why not? Well, it's because of its bonding environment. This is just one acidic hydrogen. This is a non-acidic hydrogen. When we think about Lewis acids and Lewis bases, a Lewis base is defined as a electron pair donor, and a Lewis acid as a electron pair acceptor. And so how is this a Lewis acid-base reaction? Can you see what's acting as the Lewis base? Tell me, and what's acting as the Lewis acid?
So the hydrogen is accepting the 2.
The hydrogen's the acceptor. It's accepting this
2
Oops, you know, I made a mistake here. Right, because this lone pair gets pushed into the S, it forms an sp3s sigma bond, sp3s sigma bond here. And this bonding pair gets converted into a lone pair. And so what's acting as a Lewis base and what's acting as a Lewis acid here?
The carbon is Lewis acid.
Not the carbon. In a way, I guess you could think of it, the carbon, but initially what has to happen here is a big vibration. A big vibration is going to push this lone pair here and flux the hydrogen. And so the Lewis base is going to be this oxygen here. The Lewis acid is the hydrogen. And so the oxygen attacks the hydrogen. Typically in Lewis acid-base reactions, we always think of the base attacking the acid. The base is going to have lone pairs to donate, and it's going to attack the acid. We normally don't think of the acid attacking the base. And so when we're thinking about Lewis acid-base reactions, we have to analyze the Lewis structure because different atoms will behave differently. So for example, this hydrogen here I wouldn't expect to be very reactive, but this one more so. And so when we analyze this, we say this is an acidic hydrogen. However, this oxygen should be a potential Lewis base. This oxygen here is a potential Lewis base because it has lone pairs. Lone pairs, negative charge density, negative charge density. And so these two atoms are basic within formic acid, and this atom is acidic. What about carbon? What would you say carbon would be? It'd be carbon would be a Lewis acid because it's got positive charge density and wants that negative charge density, the lone pair of electrons. But the problem with carbon is if a lone pair comes here, how many bonds do we add to carbon now? 5 bonds. Sometimes it's called pentavalent carbon. We don't want that, because carbon cannot have an expanded octet. And so if a Lewis base were to attack carbon, what has to happen is something has to break. And usually what it is pi bond. This pi bond breaks and the electrons go to oxygen here. Then we're okay. You might have seen this in dealing with resonance forms for carbonate. You guys remember pushing the electrons there? Yeah. Well, a similar kind of deal here. And so we formed this. When we look at this, did the oxidation states change? No. The oxidation states are still the same, not redox. And so, does this look okay to you? Does it violate the octet rule? No, oxidation states didn't change. The octet rule is fine. Everything has an octet. So does it look stable to you? You might have seen that's Professor Doucette. But anyway, here oxidation states didn't change. Everything looks good, right? Does this look stable to you? Yes? Probably not. It probably does not look stable. There's a reason it doesn't look stable to me. And it's not because of oxidation state. It's not because of
If the electron pairs
octet. It's because of
electrons on oxygen.
Yeah, it has to do with that, and we call it what? What makes it weird? When we count electrons, we count octet, we count oxidation state, and we count one more. Formal charge. This one looks weird because of the formal charges. Even though the oxidation states didn't change, everything still has an octet. The formal charges are not good because this carbon is going to have a formal charge of what? Now, when we count formal charges, remember we don't, winner doesn't take all. We split the electrons evenly.
Carbon was like this.
So carbon has 1, 2, 3, 4, 5. It's supposed to have 4. Formal charges are circled. Formal charge is going to be minus. This oxygen, plus 1. So it looks like hydronium, this. Oops, sorry. And this one is negative. Now, what's unstable about that?
Because oxygen is more electronegative.
Yeah, number one, oxygen is more electronegative, so oxygen should hold the negative formal charge. And number two, charge separation is unfavorable. Charge separation generates what's called a voltage, and the higher the voltage, the more charge separation you have, the less stable, the higher energy it is. And so this is creating a very high voltage here. In other words, a high separation of charge. Whereas here, do we have any charge separation here? All the formal charges are 0. Now, we do have charge separation because when we look at this, isn't this creating a high voltage here, right? But we compare these differently. And we never compare oxidation states with formal charges. Because if we did that, like say for example here, something looks weird about carbon monoxide. What is that? It's not its oxidation states, because the oxidation states look totally normal here. It has to do with the formal charges. What are the formal charges here? Minus 1 on carbon and so here we're generating charge separation. Whenever you generate charge separation like this, it creates a voltage, and that costs you energy. To separate the electrons like this. Now, so this doesn't look stable. We should try to get the formal charge to 0, and we can do that. If we just move these electrons to over here. If we move these electrons over here to oxygen, then it'll be 0 and 0, but it would violate the octet rule. And so the reason why this weird formal charge is stable is because otherwise we don't get the octet rule. And so this is unusual too because oxygen is more electronegative, so you'd expect it to take the electron. If there's a tug of war between carbon and oxygen should win. In this case, carbon won because of the octet. Now something else looks very funny about this, and that is this. Oxidation state says the carbon is positive. Formal charge says the carbon is negative. What is it? Is it positive or is it negative? It's negative. It's negative because the electron count here shows clearly that carbon has an extra electron, so this kind of charge is a real charge. This is in this case would be the apparent charge on this. Now, does that mean it's wrong? No, it doesn't mean it's wrong because of the way we use these numbers. The way we use these numbers is to compare oxidation states with oxidation states and formal charges with formal charges. But that's a real charge on carbon, and this is what makes carbon monoxide a very powerful Lewis base. Carbon monoxide is a strong Lewis base because of the oxygen in carbon monoxide or because of the carbon in carbon monoxide. What makes carbon monoxide such a powerful Lewis base? You'd say because of the oxygen that has a lone pair? Well, a Lewis base, you want negative charge density. And so which one would you say has the negative charge density? The carbon or the oxygen? The carbon. It's the carbon. The carbon definitely has an extra electron here. And so it's because of the carbon that makes it a very powerful Lewis base. And we've seen this, carbons with a negative charge. Another example of that would be cyanide. You know, cyanide is an extremely powerful Lewis base because it has a carbon with a lone pair and a negative charge on it. And so using these numbers can be tricky sometimes, especially when you get some conflicting thing like this. But when you look at the formal charges are the charges. In the oxidation states, we compare to other oxidation states here. And so these formal charges are the charges on these specific atoms here. Does this look like a very favorable structure to you? No. And so this is highly unstable, and what can happen is this carbon can pluck the hydrogen back off, leave this lone pair. So, you know, just a reverse. This carbon plucks that hydrogen and leaves these electrons behind. And then we can regenerate what we started with. And so what this means is we're going from something fairly stable to something quite unstable. You know, in order to do that, the activation energy is going to be kind of big here. And so if this is the first step of formic acid decomposition, then it's not going to be so favorable because too much energy costs. And so what could happen is, you know, this potentially what could happen is this HOH group with the positive oxygen here is unhappy, terribly unhappy, and then pulls these electrons off, generating H2O. But that leaves the carbon with this negative charge and less than an octet. And so in order to satisfy that, well, the negative charge, we're going to lose that. And so we end up with something like this. But this isn't so stable. This isn't so stable because this is a violation of the octet rule. In order to satisfy the octet rule, we need to triple bond it. And then we'll get our carbon monoxide. And water. This is what we would call the mechanism for the reaction. Mechanism, you know, there are different mechanisms, types of mechanisms. One of the types of mechanisms is where you just collide the two. It's like NO plus NO. You know, what does it form? When you take some guesses at what the stable product might be, like, you know, maybe it's N2O2, maybe it's N2O and an O. You know, we try different things. In this type of mechanism, we take that a step further. And the step further is we look at how the electrons are actually rearranged within the molecules or between molecules in order to get to the product. And so this is called the mechanism as well. And this mechanism is going to have a fairly high activation energy because this is quite unstable here. And so therefore this reaction should be fairly slow. What we're going to look at next is what if we add some acid to this? If we add some acid, then we call acid catalyzed formic acid decomposition. And so if we think about adding an acid to an acid, I have formic acid, and now I'm going to add some acid, H plus to this. And so an acid plus an acid should make what? Will one acid attack the other acid? You know, when you think about Bronsted acids, you know, Bronsted acids, they both want to give up the proton. If they both want to give up the proton, then who's going to take it? If both acids want to give up, maybe not. You know, so normally when we think about an acid plus an acid, we think about the mixture. This is a mixture of two or more acids. But that would be in the Bronsted sense. And so when we did this, let's say, for example, in chapter 16 or chapter 17, a mixture of two acids, a strong acid and weak acid, yeah, the strong acid dominates. That's going to dictate the pH. Weak acid is barely hydrolyzed, right? Okay, but this is going to be a different thing because now we're looking at what other potential reactions could occur. And so maybe it's not going to just be a physical mixture between a strong acid and a weak acid. Maybe it's going to be something more to it. And so what we'll do is in looking for Lewis acid-base reactivity, we have to look at the Lewis structures. And so looking at this Lewis structure, we already assigned these. This oxygen should be acidic or basic? Basic. The Lewis base. This hydrogen. This hydrogen could potentially be a Lewis acid. This hydrogen definitely is a Lewis acid. This one's easy to pluck off. This one is difficult to pluck off, because of the bond. So it's very difficult to pluck off here. Bond and bond polarity. This carbon should be Lewis acid. This oxygen, base, and this we already said. And so what we have is we have a strong acid, H+. Now we got to figure out what the Lewis base is going to be. We have two choices for the Lewis base. This one could attack the hydrogen and pluck the proton off, call it 1, or this one can attack and call it 2. And so either oxygen can attack the proton. Well, what typically happens is that one of these will lead to product, the other will lead to a dead end. It just goes back, something not stable. And so which one do you think is a better Lewis base? This oxygen, terminal oxygen they call it, or the bridging oxygen? Terminal, 1? Okay. So if one proceeds, then we end up with something like this. H, C, O, H, O, H. So what happens to the formal charge? Anything? The formal charges.
There's oxygen.
Yeah, this oxygen's formal charge changed. Let's count it now. So it's 1, 2, and split these. 3, split these. 4, 5. It's got 5 electrons. It's supposed to have 6, which means it's going to have a plus formal charge. Well, let's compare the two steps. If you compare this step up here with this step down here, which one is going to cost you more energy? This one or this one? Why would you say the one on top? You'd say this one would cost you more energy because, or why would you say this one here?
Take those electrons from carbon and bring them to oxygen.
Yeah, or actually the opposite. You take the electron from oxygen and give it to carbon, and they're right adjacent to each other. And so carbon essentially is taking an electron from oxygen. Does that make sense? It should be the opposite, right? Oxygen is more electronegative. And so this is what we call a charge separation. Separating charge like this costs you a lot of energy. Because when you have a high voltage, you don't want what tends to happen? When you have a very high voltage, then there's something pulling electrons one way, something kind of pushing electrons the other way. And so what happens is you can get a shock. The shock would be the electron would just transfer back. It would be the shock. Whereas over here, are we really separating? No, we already had this positive charge. Now it's attached here. And so we don't see that charge separation here. This is just positive now. But there's no negative here. And so for sure, this one is going to be lower in energy because we aren't generating this separation of charge. Well, that's going to result in a lower activation energy, which should result in a faster reaction. And so looking at this, and then we just carry it through. But sometimes what happens is we just end up at a dead end, and we don't get anything stable. And so that's what happens if we attack one here. But if we attack two, that is this oxygen 2 here attacks the proton, then we end up with something like this, which also looks like a dead end, but it turns out not to dead end. Like that. All right, so this is going to give us a formal charge now on this oxygen here. And then what can happen is that this can pull on the electrons here to form something that's quite stable. It'll be water. And so this bond breaks, leaving the electrons with oxygen here. But that puts the formal charge on. Okay, now oxygen has lost the positive charge, but now the positive charge is on carbon. Well, one way to get rid of the formal charge on carbon here is if this oxygen, actually there's different ways, but this oxygen either gives electron density there or this hydrogen gives electron density here. Which one do you think will be easier to pull electron density off of? The hydrogen or the
Hydrogen.
Hydrogen is less electronegative than oxygen, so probably this pulls the electron density here. So let's go with that. You know, all this could be happening at once as well, but like this, right? If this carbon pulls the electron density off there, sorry. Pulls the electron density from this hydrogen, we end up with this structure. But this structure, there's a problem with this structure. And what is the problem? If you look at the formal charges are great. Right? The formal charges are 0 and 0. The problem with this structure is what? The oxidation states are fine. You know, carbon is +2, oxygen is -2. That's fine. The octet rule. And so the final step for this is screwing up the formal charges. Now we got this charge separation, which is unstable. But it's better to have this charge separation with these formal charges than it is to have less than an octet. Right, so this is called an acid-catalyzed formic acid decomposition mechanism. Here the acid's being consumed, here it's being regenerated. But what this is going to do is it's going to lower the activation energy considerably because we don't have to form something this unstable. And so when we lower the activation barrier, it just speeds up the reaction. So this reaction will occur much faster in the presence of acid than without. All right, this is the last part of chapter 14 that I wanted to cover, but this kind of mechanism is not going to be on the test. You know, there are different ways you can rearrange things. You know, sometimes things happen simultaneously as well. But this is one of the reasons why I didn't talk about Lewis acid-base reactions initially. You know, during the first week or first 2 weeks of class, I skipped Lewis acid-base and just talked about Bronsted acid-base reactions. The reason is because Lewis acid-base reactions you usually do mechanistically like this, figuring out what gets attacked by whom. In fact, in organic chemistry, formic acid is an organic chemical. In organic chemistry, you do a lot of this. Pushing electrons around, looking for acidic sites and basic sites, that type of stuff. All right, for predicting chemical reactions, if you go back to the first week of class, you know, to properly predict reactions, we need to know the thermodynamics Thermodynamics is what we called the driving force earlier. We need to know the driving force for this. And we need to know the kinetics. I'm not sure if I talked about this. Did I? Yeah? No? And so let's show that here. Did I talk about metastable last time? No? There are two forms of carbon that are quite common, diamond and graphite. Which form is more stable, diamond or graphite?
Diamond.
Graphite is actually more thermodynamically stable. Graphite. And so there should be a driving force, you know, because things tend to go from less stable to more stable in terms of energy. And so diamond is a higher energy form of carbon, graphite's a lower energy form of carbon. And so we want to go from less stable to more stable. We have a driving force. But you worry about your diamonds decomposing to the graphite? No. You don't worry about it because even though we have a thermodynamic driving force, the kinetics of this reaction are very tough. Because in order to go from diamond, which is all sp3 carbons, so we have this tetrahedral network of carbon atoms, so we go from all sp3 to all sp2 carbons. In these sheets. And so to convert sp3 carbons to sp2 carbons, what do you have to do? You have to break all the sp3 sigma bonds and replace them with sp2 sigmas and pb pi's. Right, if we're looking at valence bond theory. In order to break sp3 sigma bonds in carbon, that's going to cost you a tremendous amount of energy. And So what happens is the activation energy for this is through the roof pretty much. This would be the activation energy. Since the activation barrier is so high that even though diamond is not thermodynamically stable, we call it metastable instead. So this is metastable. Metastable, what that means is it means this. It means it's thermodynamically unstable. But kinetically stable. Metastable. So diamonds are metastable. There are other examples of metastable things, lots of them. Can you give me an example? How about methane and oxygen? Methane and oxygen is an unstable mixture. There's a thermodynamic driving force to convert methane and oxygen to carbon dioxide and water. Carbon dioxide and water are a lot more stable. CO2, H2O. And so when I look at the delta H for this, the delta H, and we have the drop in energy here, delta H. You know, H is called a state function. Do you know what state functions are? State functions only depend on the final state and the initial state. And so the difference in energy between CO2 and water just depends on the energy here versus the energy here. That's our delta H. But kinetics depends on the path. Have you heard of state functions versus path functions? So delta H is a state function, but Q and W and those type of things are path-dependent functions, and the mechanism is path-dependent as well. And so, you know, what we have here is, you know, I don't know how many steps there are. There's a bunch of steps here, but basically, the activation energy, if you look at the biggest step here, maybe this one here, even though this looks taller, this has to be up the baseline here, so this is the next activation energy, which is big. It depends on the mechanism here. And so methane and oxygen, this is metastable. Metastable. It's metastable at 298 Kelvin. Because at 298 Kelvin, you know, if I fill this room up with methane, do I have to worry about an explosion or fire immediately? No, because it's metastable. But if the temperature were a little higher, then that would give more kick to the molecules to make it over this hump and down the other side, which would result in a fire or explosion. And so here, this is metastable because we have a thermodynamic driving force. We're going down in energy here, but kinetically, it's stable under these conditions. We can change the conditions and make it quite a bit more reactive. So next, all right, so can you remind me of the driving forces? Yeah, driving forces for chemical reactions. Just go back through those and then let's take a look at those driving forces. And these are, you know, what we call thermodynamic driving force. Just as a review, and, let me do one thing. Then tell me what all those driving forces have in common.
We started next chapter. Wait, what is he doing?
We're supposed to be finding driving forces, and what's the similarity between them?
Mostly I think, but I stopped for a while, but I have some like right here on the inner. Yeah. I only realized yeah. They don't ever end. Like when we first get them. I don't get them. Like when we first get them, they're like,
Not here.
I like to cut my wrists.
We're sold for this place now. Well, you don't take it this summer. Oh, okay. Next semester is summer.
I took one
David, are you transferring your
Nobody wants to do video.
I know
April 24th. I think for Berkeley. Oregon, you just sign a bar for you. That's my yeah. I mean, like, I hope I get into like San Diego. Hey, if I get to LA or Berkeley, hello. Probably Berkeley. LA is too close. Well, I mean, you always come in next year.
Why didn't you?
Why did you apply this year?
Because this is my first year.
Oh, yeah, right.
Some of us have been here like 4 or 5 weeks. I'm just saying, I haven't been So you're in 10 class?
No, I'm not. This is
Oh, well, then I'll be in 10 class.
long have you been? 30 years.
I don't want to be a fourth year here. We'll come to visit. We'll come to visit.
Saying that right now.
We'll come in the summer. We'll come in the summer. You like surprise. I know you can't replace us, but
Psychology.
I don't even have you on Facebook.
Dave, do you have Facebook?
Oh, right, ask me on Facebook. Ask me on, okay, here, I'll add you on Facebook. That's right, you reactivated it.
Basically,
No. Two in one shot.
One shot, one kill.
Yeah.
I like that.
Yep.
No? No? Wait, you mean play LA? Wait, but then you see they're like all the same though. What do you want to do? Study?
Okay, David, D-A-V-I-D.
Are you adding people on Facebook?
Yeah.
be a surgeon. So that's like
You're not
it's not like how they portray it, it's how they're just put up. They're like the smartest of the smart.
Let's see if I meet. Let's see.
Are sure you get the right one? You get the right one. Like you.
I don't think you can find me. I get a hack
S-H-A.
Shop, no, S-A.
Okay.
H-A.
Yeah,
Okay.
my
A-W.
sister's friend is like almost a doctor. He's taking his final exam, and then that determines whether what he has to what he can do.
Oh, you think to rush?
And then like, oh,
I mean, are you high?
he goes to the high school surgeon. And then basically he becomes a surgeon. That's
I thought you went to St. Lawrence. Like south or something.
He's like studying right now. Like,
Let's see if I can find myself.
Hey, where did they feel like disappear?
this that dude's like fucking like 32. He's like 27.
You want friends? Oh, you can't even add me to it? Oh, like, is there even an option here? I can hear all that I do.
I just want that. Yeah.
Last name?
Tell you that
A-W?
Yeah.
Are you with like two other people?
Yeah.
yeah.
But you're talking about.
Yeah, that is you. That's right. Thank you. I
And after that, you really want to go for it, then go for a journey that is basically yeah, fellowship. I feel like
All right,
from Chem 1A, we had a bunch of driving forces.
That's why we're just going for 120 a year.
So if we have a metathesis reaction, what are the driving forces for metathesis? Gas formation, precipitation, strong acid to weaker acid.
Electron transfer.
Okay, if we have electron transfer for metathesis, or electron transfer would be called redox. So if we have a redox reaction, what are the driving forces? Gas formation, correct? No, gas formation is not a driving force for redox.
Only for metathesis.
Only for metathesis. Gas formation works for redox, may work for acid base, but actually doesn't work for redox. It doesn't work for redox because if you think about gas formation, if we have two H2O liquids going to two hydrogens plus an O2, is there a driving force for that? Because I'm going from a liquid to 3 moles of gas. Driving force? Good driving force for that? No. I mean, water, we shouldn't see this decomposing. 2 moles of water, liquid water is 36 milliliters. 3 moles of gas is about 75 liters. You know, and so we're taking 36 mils and creating 75 liters of gas. Do you see that happen often? No. So what is the driving force for this? Yeah, it would change the world. I mean, that would be explosive. Sure. It's going from stronger to weaker, oxidizer, reducer. So water is fairly stable, but hydrogen and oxygen, is that a stable mixture? If I filled this room up with hydrogen, would it explode immediately? Probably not. It probably wouldn't explode immediately because a mixture of hydrogen and oxygen is what we call a metastable mixture. And so if you have a hydrogen and oxygen, what it needs is it needs a little push to get over the activation barrier. What's that little push? A spark or a hot surface. And so hydrogen and oxygen, this is very unstable. Very unstable meaning it's highly reactive. Highly reactive means it's a stronger reducing agent, hydrogen, and a stronger oxidizing agent going to a weaker oxidizing agent, weaker reducing agent, which water is. One of the waters is acting as an oxidizer, the other is acting as a reducer. And so there's no driving force for this. We expect the reverse reaction to be favorable. And so no driving force in the forward, the reverse has a driving force. This is a thermodynamic driving force. And the thermodynamic driving force for this is very big, except we got that little hump. That little hump keeps it stable. But would you feel comfortable in a room filled with hydrogen and oxygen? Probably not, right? Because you're going to have a big fire explosion. And then acid-base reactions. Acid-base, we're going from stronger acid to weaker acid. Now, what do all these have in common? All these have in common, the driving forces are all shared. We're going from something that's
Stronger to
weaker. In other words, less stable to more stable. That would be a driving force. And when we talk about stable, what in particular is stable about these?
Less reactive. Less energy.
Yeah, less energy of what? Typically, what we're talking about are bonds. And so we have less stable bonds going to more stable bonds. And therefore, back in chapter 7, you have this equation. Delta H for the reaction can be estimated from the bond energies. If we sum up the bond energies, for the reactants minus the sum minus the sum of the bond energies for the product. So if the products have a stronger bonds overall than the reactant, then this number is going to be bigger. The bond energies are greater. If this number is bigger here, it should be exothermic. And so that means we're going from higher energy to lower energy. Delta H is going to be less than 0. And so something like this would be hydrogen and oxygen. Hydrogen gas and oxygen gas going to H2O liquids. So we would have something like this. Delta H would be less than 0. So in this reaction, we're looking at in this chapter, we're looking at spontaneous reactions. Spontaneous reactions occur naturally. You don't need any external force to get them to occur. No external force required. And so we need to ask ourselves this question, and that is, are all exothermic reactions spontaneous? Maybe that's another way we can judge the driving force of a reaction. Maybe we don't have to memorize all that other stuff, right? As long as we can predict, hey, if this reaction is exothermic, then it's spontaneous. And so are all exothermic reactions spontaneous? In the scientific method, we look for patterns, and if those patterns form a consistent trend, we could call it a law. And so maybe this would be the law of chemical reactions. The law is that if it's an exothermic reaction, it's spontaneous, it has a driving force. It's going to occur naturally. And the answer is no. But isn't that what we're looking at in Chem 1A or at the beginning of this semester? Yes. Yeah, that was what we were looking at. And so what's the difference now? Because before I told you these things are going to drive the reaction. Gas formation, precipitation, because those are forming more stable stuff, stronger to weaker. It's forming more stable stuff. And so all the driving forces I told you were forming more stable stuff. So forming more stable stuff should be exothermic in terms of energy. And it turns out it's a little bit more complicated. For the reactions that we looked at, it works. What I told you works, but for the reactions we looked at, that's not a comprehensive list of reactions. I mean, it is a comprehensive list in the sense that we looked at the 3 types of chemical reactions, right? The 3 types. But there are some reactions within those 3 types that don't behave necessarily as you would expect. It turns out one can think of 2 driving forces in nature. These can conflict And so one driving force is we want to minimize energy. And that's what we've been talking about, minimizing energy, going from things that are less stable to more stable. And so energy could be delta H. If we minimize delta H, we want it to go down in energy, so it should be exothermic. So delta H less than 0. That's good. Minimize energy. In other words, we want the energy to decrease. We have delta H, but we also have U. Do you remember delta U? Delta U is not just potential, but it would be called the total internal energy. And so delta U would be the change in internal energy. If the change in internal energy is less than 0, that's good too. In other words, we want the internal energy to decrease. So what's the difference between internal energy and enthalpy? Are these two saying the same thing, or is it different?
It's different.
Okay, if it's different, in what way is it different? Maybe in what way are they similar? And so we'll need some review of this. Actually, you could review the difference between enthalpy and internal energy. We'll talk about it briefly, but if that doesn't click, then make sure you go back. Actually, they're basically saying the same thing. You know, if we want the energy to go down, it's either the enthalpy or the internal energy we want to decrease. Basically the same thing, but one is a little bit more restrictive. Which one is a little bit more restrictive? Internal energy is non-restrictive. No restrictions on that. And so it is actually the enthalpy that's a little bit more restrictive. We'll talk about that. And so this is it. Precipitation. Precipitates are stable, strong bonds, etc. But one thing we didn't look at is this. We want to maximize entropy. Entropy is given the symbol S. And so we want any changes in entropy to put positive. That would increase the entropy. Now, what is the entropy? The entropy is a measure of the disorder. In other words, the more disorganized, the more disorder there is, the more favorable. So we want to increase the entropy, make it more disordered. So both these things are going to drive our reactions. What's easier for you to determine, delta U or delta H? What's easier? Delta H is easier. Because there are a lot of ways to determine delta H. Do you guys remember all the ways to determine delta H? What would you say the easiest way to determine delta H is? I'll leave that. If somebody asked you to determine what is the delta H for this reaction, what would the first method you'd probably go to? What would that be?
Differences between the bond energies.
Difference in bond energies? Yeah, that's probably pretty easy. But the difference in bond energies, you know, the delta H of the reaction, I wrote these squiggly lines to represent that. It's the difference, delta H of the reaction can be estimated from the difference in bond energies. The sum of the delta H of the bond energy for the reactants. Normally it's products minus reactants, but you know, to keep it the sign convention right, it's reactants minus delta H of the bond energy. energies for the product. This is probably, you're right, this is probably the easiest. You know, one of the easiest ways to determine delta H, but there's a problem with it. You know why it's only an estimate? Why it isn't more accurate? It's not because of entropy.
Because the energy value for the bonds themselves are an estimate to begin with.
Yeah, right. The bond energies that we get from the table
They're just averages.
are average. And when you have an average, there could be a spread of bond energies, you know. Let's say the average HO bond is 439 kilojoules per mole. Does that mean every single HO bond is going to be 400? No, it depends on the molecule. Even for H2O, this is the example they give in the book. If you break the first bond, it's going to cost you a certain amount of energy. So once we break the first bond, is this breaking the second bond going to cost you the exact same amount of energy? No, because the electron density has been rearranged, so it's not going to be the same. And so what they do is they average a whole bunch. You know, they look at formic acid, for example, and break the HO bond here. Is that going to be the same energy as in water? No. And so we got a wide spread. When we got a wide spread like that, and we're just using averages, then that's not so accurate, right? And so tell me the easiest way to more accurately determine delta H.
Wasn't it like Hess's law?
Yeah, Hess's law. There are two variants of Hess's law. Was it Hess's law adding up the equations, or Hess's law? You remember adding up the equations? You just add up the delta H's, but adding up the equations is kind of a pain because you got to make sure that the things cancel out properly, and that you end up with the correct coefficients on all the reactants and products. And so it's not so easy. It takes time, you know, if you're doing a Hess's law problem. Unless it's simple, like adding just two equations. But when you have to add up 2, 3, 4 equations together, it can get complicated, especially with fractional coefficients. Right? And so there's an easier way. What's the easier way of determining what delta H is accurately? Yes, that's it. It's a Hess's law application, but rather than using any old reaction, you're only using formation reactions, right? Do you guys remember that? And so if you're going to determine delta H, probably the best way to determine delta H is delta H of the reaction should equal the sum of mu P times the delta H of formation of the products. And so this is now correct. You know, it's usually products minus reactant. So minus sum of mu R delta H of formation of the reactants here. So we just got the products minus the reactants. This. Are there any other ways to determine delta H? How about experimentally? If you wanted to determine it experimentally, rather than using, where do we get these delta H's of formation? Appendix D. You could also determine delta H experimentally by using calorimetry. Would you use constant pressure calorimetry or constant volume? Or you could use either. You could use either, that's correct. But which one would give you delta H directly?
Pressure.
Constant pressure. And so from constant pressure calorimetry, would you get delta H? Constant volume calorimetry usually gives you not delta H. It might give you delta H, but typically it gives you
Delta U.
delta U. And so to answer the question, which one do you use more of? Delta H. Why do you use delta H mainly? Because delta H is restricted to constant pressure. Right? Delta H has a restriction. What do you do most chemical reactions under? Constant pressure conditions or constant volume conditions? constant pressure. We don't do chemical reactions in bombs all the time, you know. And so we're going to do it out in the open, so we use delta H. And so you'll need to review a little bit more because we need a more in-depth knowledge of delta H and delta E. But these we can determine. But how do we determine this? Well, one way of determining this is just qualitatively. So for example, a solid, a solid is going to have more order, less disorder than a liquid. A liquid is going to be more random as far as the positions go. And a liquid is going to have more order or less disorder than something like a gas. A gas is going to have the particles more disorder. And so we could figure out delta S qualitatively. And so let's take a look at some examples here of just delta H qualitative and delta S qualitative. And then try to make predictions about the driving force. So take a look at some homework problems. Number 5 here. 5A is carbon tetrachloride. Liquid goes to carbon tetrachloride gas. So if we go from CCl4 liquid to CCl4 gas, what is delta H for this? Is it equal, less than, or greater than 0? In other words, is energy going up or energy going down? Or maybe there's no change in energy.
Energy's going up.
Energy is going up. And so delta H is greater than 0. This should be endothermic. In other words, if you're going to boil a liquid, you have to add energy in order to get it to boil. There's another way of thinking about it. In order to boil this, we have to break. We have to break the intermolecular forces of attraction holding the carbon tetrachloride molecules together. And whenever we break anything, that costs us energy. Versus the reverse process is forming. You know, we're forming the interactions. That should be exothermic. All right, what about delta S here? Yeah, delta S, this should be greater than 0 because we're going from something that's more ordered, less disordered, to something that's less ordered, more disordered. So the disorder is going up, the entropy is going up. So that looks good. Delta S is greater than 0. This is what we call a driving force. Delta H greater than 0, we don't call that a driving force. And so on the one hand, we say this should occur because it has a driving force. On the other hand, we say this should not occur because it doesn't. And so this is no-go, this is go. And so what is it? Is it a no-go or a go for carbon tetrachloride vaporizing to a gas? And so which one of these wins here? Don't know.
Greater than signs?
I'm sorry?
Those are both greater than 0.
Yeah. Delta H is greater than 0 and delta S is greater than 0. And so we have conflict. I said that these driving forces can conflict. Now they're conflicting. If there's a conflict between the driving forces, which one wins? The dominant one. But which one's dominant? Maybe it's a tie. Enthalpy? Delta S wins? Sometimes delta S wins, sometimes delta H wins. We'll see that later. But here we can't say anything more yet. Let's go to the next one here, 5B. We go to B. B takes copper 2 sulfate, trihydrate, solid, plus 2 gaseous waters. This produces copper 2 sulfate, pentahydrate, solid. What's delta H equal to? Is it equal to 0, less than 0, or greater than 0? In other words, no change, exo or endo?
It's like less than 0.
It's exothermic? How did you figure that out? It's right, you know.
H2O gas.
Yeah. H2O gas going to solid, that's got to be exothermic, it's got to release energy. Another way of thinking about it is that the H2O gas is being incorporated in the solid. So in other words, it's forming new bonds or forming new intermolecular forces. And so when we form bonds or intermolecular forces, it releases energy, it's exothermic. If we reverse this, let's say we want to drive off the waters, then we heat it up, right? If you want to drive off the waters, heat it up, that's endothermic. And so to break the waters off, or, you know, they're probably attached to the copper, like the complex. To break the waters off the copper, or knock the waters out of the holes in the crystal lattice, we need to add energy. We need to break things. Breaking things, endo, forming things, exo. So this is forming new. So that's exothermic. And now what about delta S?
It's less than 0.
Less than 0. And so delta H, this is good because we're going down in energy. Going down in energy, that's a driving force, right? But delta S, that's bad because we don't want to be going down in entropy. And so, again, we have a conflict, you know, which wins? One says reaction, the other says no reaction. We're out of time, so we'll continue this next time, Wednesday.